Hey guys, so today we're talking about nonlinear systems of equations. Okay, so what is it? A set of two or more equations in which at least one of the equations is nonlinear. So it could be that they're both quadratics, it could be that one is a circle and one is a quadratic, but for today what we're going to focus on is when one of them is a line and one of them is quadratic. Okay, so here's the three possibilities. It is possible they could have no solution. So if you remember in linear equations, it was when they were parallel, they had no solution. In this case, it's just when they're not really near each other on the graph. So therefore, they don't ever cross. So there's no solution. Secondly, it could have one solution. So it looks a little bit like a tangent line where it just barely touches the quadratic, but just in one point. Okay, and the third one, it could have two solutions. So it is possible to have two solutions on these systems. So let's look at some examples. So of course, just like before, one way that you can solve them is by graphing. I really never think this is the most effective method, but just to show you that you could do that. Okay, so graph each equation and then find the intersection. So I have this first equation. So the same way I would find the vertex and then I would plot the vertex. And then I plotted the y-intercept and I did the reflection of the y-intercept. But in this case, I can't really just be sketching random numbers like I did before and just sketching the path, because I need to know exactly where it's going to go. So maybe I find the x-intercepts and plot those or something like that. Okay. Then to sketch the line, I can sketch the y-intercept and then just use the rise over run to go up and down the line. So then I find there's two places where it intersects. Over here at -1, 0, and over here at 2, -3. So it actually is a lot easier if you put them into graphing calculators and find the intersection, but since on the EOCT we won't be able to do that, we're not really going to use that method that much now. But we could graph it, we could find the two solutions, and once we find them over here you can check your work. So my two solutions were -1, 0 and 2, -3. So basically I can plug it back in to make sure that that is a solution to both of the equations. So I plugged both points into the quadratic, so I plugged in -1, 0 into the first equation, and then I plugged 2, -3 into the first equation, and you can see that it does actually work both times, so that does equal 0 and that does equal -3. Then I plug it into the linear equations, and both the points work in the linear equation, because if it's a solution, it needs to work for both equations. So these are the actual solutions. Alright, so moving on. Another way to solve is by substitution, so hopefully you're seeing a similar pattern here, that it's the same methods to solve, it just looks a little different. Okay, so just to kind of show you, if I sketch a graph of it, that's what it would look like, and I could also put it in a graphing calculator to check. Okay, so if I'm solving by substitution, since these are both solved for y, I have y equals a quadratic and y equals a linear, I could go ahead and just substitute them, in other words, just set them equal to each other. And once I set them equal to each other, I could just subtract this term over here. So now I'm just solving. So I'd subtract x and 2 from this side and subtract it from this side. So now it just looks like one singular quadratic equation. And from there, you should know how to get solutions. So from there, ways to get solutions are the quadratic formula. You can use the square root method, you can complete the square, you can factor. So this one factors. I took out the GCF, and then once I took out the GCF, I factored this. It was actually a perfect square trinomial. I divided both sides by 2, and I got that these were both x minus 1, so I set that equal to 0, and I found out that x was 1. And so since this is a system of equations, I got one variable, which was x equals 1. So then I plugged that back in. So you can plug it back into either equation, but it's obviously going to be easier just to plug it into the linear equation. So I plugged it in, I got 3, so my solution was 1, 3. And if you graph these in a graphing calculator, you would see the picture would look about like that. And at 1, 3, which is actually close to the vertex, is where they intersect. Okay. So, of course, the last way is going to be to solve by elimination. So solving by elimination, so you have these two equations, and one is x squared and one has an x, and so you can't combine those. Okay, so what I'm going to do is I'm always going to get rid of the y's. So when you solve by elimination, it has to be the y's that you get rid of. So what you would do is you would line up your two equations, And you would line them up in a way that the y's are lined up. So you can see I put my 4x minus y on top, and then I put the y below it. So when I add these two, you can see that the y went away, and I was left with just 4x. Okay, so the y is eliminated. I just bring down the x squared, and then I lined up my constants. Okay, so I had 4x minus y equals 2, and I just put the 2 over here so I could line up the constants. So those were eliminated, and I had 4x. I brought down the x squared, and I brought down the 3. So now I'm going to do the same thing that I was doing before. I'm going to put everything on one side. Okay, so I just subtracted 4x and then set it equal to 0. And then solve it. So I chose factoring because it easily factored. And I found two solutions. So I found out that x equals 3 and I found out that x equals 1. So then I had to go back and plug it into one of the equations. So it doesn't matter which one. I chose the linear equation. So I plugged in 3 into the linear equation and I found out that the coordinate was 310. And then in the other one, in the same equation, I plugged in 1 and I got 2. So it was 1, 2. Okay, so just to kind of go back from the beginning, if I'm going to solve by elimination, it's always the y's I'm going to eliminate, because once I eliminate the y's, I'm going to be left with the quadratic equation I can solve. So I just lined up the y's, brought everything down, so I was left with something like that, and you should know how to solve something like that. Put it in standard form and factor it, quadratic formula, etc. Get the answers, but you're used to stopping there, don't stop there, then you got to plug them in to get the solution. Alright, I'm going to give you one more example because this example is a little bit different. This is an example when you would have no solution. So if you graphed these, they would come up like this. So I want you to see what's going to happen when you try to solve one when the answer is no solution. Okay, so I start with these and I'm going to try to eliminate. So I'm going to have to line up the y's. Okay, so on this one you see I have y equals x squared plus x minus 1. So that looks the same. On here, I'm going to line up these y's, so I put negative 3y, and I went ahead and just moved the x over here so it was lined up with the x. And then the constants were lined up. So since those ones in green won't eliminate, I multiply the top one by 3, so that I then had this equation. 3y equals 3x squared plus 3x minus 1. Okay, now down here I didn't have to change anything because that already had a negative 3y. So those canceled out and I was left with 0. And then I brought down everything over here and I end up with just a quadratic equation. So if I was going to try to factor this, I would use the pants method and I would say, okay, something that adds to 1 but multiplies to 15. Okay, so 3 and 5, 1 and 15, that's not going to work. Okay, so when I see that's not going to work, what do? I go to the quadratic formula. So I plug it in the quadratic formula, and when I plug it into the quadratic formula, what do I find out? Well, the discriminant is actually negative. So, if the discriminant's negative, that means there is no solution because I don't have an x value. It's not a real number. Okay, so therefore, there is no solution. And again, if you were to put these into a graphing calculator, you would have seen this picture, so you would have seen that there was actually no solution.